Frequency response analysis of a base excited cylindrical column. This tutorial explains how to perform frequency response analysis using FEAST. The column is having a height of 1000 mm and radius 300 mm. Material properties are Young's modulus 200 GPa, Poisson's ratio 0.3 and density 7800 kg per meter cube. The column is fixed at the bottom and a base excitation of 9810 mm per second square is applied. The response at the free end of the beam is our interest. In this, we are going to generate the hexamesh directly from the volume. For that, you have to create the volume. For that, you need the axis points and the radial points. So, create the key points. Go to create geometry, key point, create by XYZ. Create key point at 0, 0, 0 and 0, 1000, 0. Create key point at 300, 0, 0. The 3 key points will be created. Now you have to create the volume. For that, go to geometry, volume, create cylinder. Select snap to point option, axis. Select the 2 axial points and select the radial point. Click apply. The volume will be created. Rotate the view and see the volume. If you click on the fill option, it will fill the volume. Go to front view. Now go to mesh, FE mesh, hexa. Select the volume. Enter the element size as 50. Click on divisions. Adjust the divisions on each side. As required, select sweep. Click apply. The volume will be meshed with brick element. Erase volume. Select volume, the volume will be erased. Select fill option. The filled view of the elements will be displayed. Pick rotate view and rotate the model in different directions. Go to displacement, boundary condition, add. Go to front view. Select all the node IDs at the bottom. Arrest UX, UI, UZ degrees of freedom. Go to property, material isotropic, add. Select all the elements. Click on material data. Enter the Young's modulus value as 200,000 and Poisson's ratio as 0.3 and density as 7.80 minus 9. Click OK. The material property will be assigned. Go to analysis option. Analysis type as frequency response. Click apply. Go to analysis, frequency response, general, add. Enter the number of modes as 20 and select the node list. A response is to be calculated. Select all the nodes on top of the column so that the responses at all the nodes on top of the column will be calculated. Enter the start frequency as 1 and the maximum frequency as 500. Select finer increment as 1 and coarser increment as 10. Select mass option as consistent and click apply. Now go to save the model. Save the model in a directory where you want. Save using a suitable name and save. You have to enter the damping value. For that, go to frequency response, damping, add. If you click on edit, frequency gen, set 1, it will display the entered frequency response general data. Go to frequency response damping, select frequency. For frequency 1, enter the damping factor as 0.02. For frequency 10, damping factor 0.02. And for 1000, 0.02. Click OK. The explicit damp value will be added. Go to Analysis, Base Excitation. Select all the node IDs at the base. Enter the acceleration value as 9810 mm per second square. Select component direction as UX. Click Apply. A base excitation is assigned at the bottom. Go to Front View. Select Fit to View. Save the model again. Click Save and run solver. Confirm Yes. The status of solver will be displayed at the bottom right corner. After completing, it will show finished successfully. Go to Post, View Results. Click Frequency, click Apply. It will show the frequency values. Go to History Plot. Select Acceleration. Select Component T Resultant. Pick a node on top of the cylinder where you have requested the output. The acceleration versus frequency value will be displayed. Click a point on the curve. It will display the frequency and acceleration at the corresponding point. Pick velocity. Click Apply. It will show the velocity versus frequency curve. Click Displacement. It will display displacement versus frequency curve. You select on Zoom option and select using rectangle selection. It will zoom in particular region of the graph.